Hello girls and boys, this is Daniel for Rock the JVM, and in this video I'm going to talk about racing fibers in Cats Effect 3. Now, this video is more beginner friendly, so I'm just assuming that you're getting started with Cats Effect 3 along the lines of, I heard about Cats Effect 3, or I've just spent maybe half an hour on their documentation page. So if you've done that, then I'm assuming that you're just getting started with Cats Effect 3. Now, optionally, I recommend you watch the previous video on Cats Effect 3 fibers, where I introduce how fibers work, how you can start, join, and cancel them. So this is quite important for this video. And as always, I recommend that you code with me because I write code from scratch, obviously. And whenever you need to refresh your memory or just get back to these concepts or to the examples that I'm showing you here, just refer back to this video or to the written form at the blog, of course, with the link in the description to this video. All right. Now, without further ado, I'm going to get back to my code, and I have here a Scala 3 project, and because I'm using a release candidate of Scala 3, so Scala 3 is not released yet at the moment of this recording, in IntelliJ, I've added my imports myself because IntelliJ isn't really smart enough to do autocomplete for me. And if you want to write code with me in this video, you can either use Scala 2 or Scala 3, and I'm going to tell you what you need to do if you want to write code for Scala 2. And in particular, if you want to use Cats Effect 3, you'll need to go to your build SBT file and add the Cats Effect library here. So org type level %% Cats Effect, and I'm using Cats Effect 301, but you can use 310 at the moment of this recording. This is the latest version. And here, after you add it, just click on SBT refresh or click whatever pop-up IntelliJ shows you so that the library is downloaded correctly. Now, I'm going to get back to my application. I've defined an object here that I called racing IOs, and I'm going to extend a special type in Cats Effect called IO app. An IO app is kind of like the Scala 3 standard app, where the main method is called run, and it takes a list of string as an argument, but instead of returning unit, it returns an IO data type. And you probably have heard about IOs because this is the first thing that you read from Cats Effect 3, or Cats Effect of any version for that matter. Now, I'm going to use a special flavor of IO app called ioapp.simple, which instead of an IO that returns an exit code, we are going to return an IO with units. So the method that we're going to implement here in order to make this application runnable is to say def run, which returns IO unit. And you probably remember what IO is. It's the crucial data type in Cats Effect. It describes any computation that might have side effects and that might end with a value of type A. And this data structure is very powerful. It has all kinds of combinators, including map, flat map, and so on and so forth. You can do 4 comprehensions on them, and you can treat them like you do options and other data types that you might have worked with in your day-to-day Scala work. And if you want to create an IO, I'm going to create the meaning of life, which is a real passion of mine, as an IO int, and you can use the constructor or the factory apply method for IO. I'm going to use IO42. Now, in order to actually see something to the console, in the previous video where I discussed fibers, I added an extension method to the IO data type where I also print the value contained in that IO and also the thread on which that IO was evaluated. So I'm going to replicate that here. So I'm going to use an extension method. So I'm going to say extension, and given a generic type A, I'm going to decorate an IO of type IOA with a method that I call debug. And this debug method returns the same data type, and I'm going to use the map function on the IO, so I'm going to say IO map, and given the value contained in that IO, I'm going to print something to the console, so I'm going to print line, and I'm going to use thread, current thread, get name. So I'm going to print the thread on which this IO was evaluated, and I'm going to wrap that inside some square brackets so that I can isolate the thread name from the value. So I'm going to inject the value inside as well, and I'm going to return that same value. So I'm going to simply decorate this IO with some additional print line statements. Now, if you want to print this value 42, all you have to do is say meaning of life dot debug. So this will be an IO int, and after that I'm going to use void. Now, the void function is essentially a map in which you turn the value inside, the value, into the unit type that we require for the main application. So if you say map value arrow unit or say void, this is the same thing. All right, so I'm going to use meaning of life debug void, and if I right-click my IntelliJ because it runs a release candidate of Scala 2, of Scala 3, it doesn't really have this context run method, but depending on when you're watching this video and if you're using a final version of Scala 3, you're surely going to have an option to run your application, but I'm going to use Control-R to run my application here from my keyboard. And notice that I have IO compute 2, this is the thread on which my IO was evaluated, and I have the value 42 printed to the console. All right, cool. So with this background already set, I'm going to teach you about racing. And in the previous video where I introduced the concept of fibers, you know that these IOs can be executed on the calling thread, that is on the main application thread. But in the previous video, I showed you how we can execute or evaluate these IOs on other threads via a concept called a fiber. And a fiber is like a lightweight thread, and you can spawn millions of these small fibers on the same JVM because they're simple data structures. And the cancellation runtime and thread pool takes care of scheduling those fibers for execution. So you get massive parallelism with just a bunch of threads. Now, assuming that you know what a fiber is, I'm going to teach you how we can race two IOs. And the concept of racing in general means that two computations run at the same time and reach some sort of common target, such as modifying a variable, computing a result, or whatever else. And in our case, we're interested in the IO which finishes first from two possible IOs. So let's consider two IOs. One tries to compute a result and we'll simulate that with a sleep, and one triggers a timeout. So I'm going to have a valuable IO, which is an IO int, and I'm going to say, and I'm going to print some debug strings so that we can see something into our console. So I'm going to say IO with, say, task starting, and then I'm going to call debug, and then I'm going to sequence that. So I'm using this star greater than operator, which means sequence, or and then. This is implemented in terms of flat map, and I'm going to say IO sleep with 1 second. And the second method is available on the int type via this import, Scala concurrent duration underscore. And then I'm going to sequence that further with an IO, say, task completed. And then I'm going to sequence that with an IO returning an actual value. So I'm going to use 42. All right, so I'm going to sequence all these IOs, and the final value, it takes the value of the entire expression. So this valuable IO is an IO 42 after chaining all these IOs together. And the value 42 is obtained after 1 second. And I'm going to decorate this IO with a cancel listener. I discussed in the previous video about canceling the fibers executing or evaluating IOs, and I'm going to print something to the console if this IO ever gets canceled. So I'm going to call this VIO, still as an IO int, and I'm going to decorate that as valuable IO.onCancel. And onCancel takes an IO that returns unit. So this is, I'm going to use IO task cancelled. And I'm going to say debug and then void because we need to have an IO unit inside these parentheses. All right, so I have a valuable IO that I want to compute a task, and if this task ever gets canceled, this thing will be printed to the console. All right, now I'm going to create another IO that I'm going to call timeout, and I'm going to have an IO unit here, and I'm going to print pretty much the same things with some timeout. So I'm going to say timeout starting, and I'm going to also sleep. So I'm going to have IO.sleep for, let's say, 500 milliseconds. So I'm going to say 500 millis. And then I'm going to sequence with IO, say, timeout, ding ding. And then I'm going to use debug and then void, so that I return IO unit, and I'm also going to make sure that the first one also gets a debug so that I can see the output to the console. So I have two IOs this VIO and this timeout that I want to run on two separate fibers, and if this timeout succeeds, that is, if the timeout elapses, then I'm going to cancel the fiber running this other one. Now, cancellation 3 has a concept of racing, and I'm going to define a method called testRace, and I'm going to do the following. I'm going to say val, let's call this first IO, as io.race. And io.race has two arguments, or takes two arguments, and I'm going to use VIO and the timeout. Now, this expression returns another IO, and the type returned or computed by that IO is an either with either the type returned by the first IO or the type returned by the second IO. And in our case, it's either with int and unit. And in general, io_race returns an IO with either A or B. And A is the type returned by the first IO, and B is the type returned by the second IO. And of course, either of those can win, and so io_race returns an IO containing an either A or B. Now, because this first IO is an either wrapped in another IO, I want to say first IO dot flat map, and I'm going to use a partial function here in case I get the left side of an either. Let's call this left with a V, and the V must be an int, so this is the type returned by the valuable IO. I'm going to say IO with task 1, and I'm going to inject the value V inside here. And obviously I need to test the other case. I'm going to use write with whatever, because that whatever is going to be unit, and I'm going to have an IO saying timeout 1. Okay, so we have task 1 with a value or the timeout 1. Now, how do we use this? This testRace is going to be an IO string, because this is the type that we are returning on either case, and so I'm going to return an IO string at the end. Now, if we want to test this one and see the output to the console, then we would use testRace debug void. All right, so I'm going to have testRace, which uses the VIO and timeout, and then I'm going to call debug and then void. Let's see if we get some duplicate results, and then void to turn that into an IO unit. Now, obviously, if I right click, I don't have the option, so I'm going to use Control R to run my application. Now, look at this output. So we have timeout starting and task starting both at the same time and both on different threads. So we have IO compute 4 and IO compute 10. That means that io_race starts both IOs or evaluates both IOs on different threads. Now, notice that timeout, the ding ding thing, is evaluated on yet another thread. That is because the IO sleep yields control over the current thread. And we have task cancelled, which is our listener at the very beginning. So we have this on cancel thing being triggered, and then we have timeout 1, and we have the IO returned by the race, and I'm going to call debug so that we can see the output there to the console. So this is what happens. The timeout and the task are both starting, the timeout triggers, and the task gets cancelled. Now, it's always good practice to have the kind of listeners here, like on cancel, attached to the IOs which handle resources, because in the case of cancellation, which is our case, of course, these resources that the IOs might use, those might leak. And there are many tools for handling resources, such as manually adding on cancel, like in this example, or using the bracket pattern, or using the standalone resource type in cancellation. I'll talk about all of them in detail in the upcoming cancellation course. And the estimated date for release for the cancellation course is close to the Scala 3 release date, somewhere late May, hopefully. Fingers crossed. And I'm going to talk about all of these patterns with on cancel, with bracket, with resource, which is better, and when you should use each with every possible use case. Now, this timeout pattern is so common with starting a task and then starting a timeout and then canceling the task if that time elapses. This pattern is so common that the cancellation library offers a dedicated method for it, which is called timeout. So I'm going to define a val called test timeout, as an IO int. And I'm going to, first of all, I'm going to spell int properly. And then I'm going to use the VIO, this valuable task, and I'm going to call dot timeout with a duration like 500 millis. This essentially does the same thing as our test race function, except the timeout will not only cancel the IO, but will raise an error in the resulting IO. So if the timeout elapses before the task gets finished, the entire IO will raise an error. So if you want to see the result here, I'm going to use test timeout, and I'm not going to call it, I'm going to use it as is, and I'm going to run the application for you to see what happens. So notice that we have task starting and task canceled. So if the timeout elapses, then the original task gets canceled, but the final IO results with an exception. And we saw earlier how you can raise exceptions in the previous video. All right, now there's one last thing that I want to show you, and this is a more powerful version of the IO race combinator called racePair. And similarly to racePair will start two separate fibers for the two IOs that you want to race. But unlike racePair does not cancel the losing IO. racePair gives you back the fiber of the losing IO, and you can choose what you want to do with it. And because either IO can win, the result is a little bit more complex. So I'm going to show you an example. I'm going to have a demo racePair. And I'm going to take a type argument A. I'm going to make this more general. So I'm going to have an IOX as IOA and IOY as IOA. And I'm going to call racePair on these two items. So I'm going to have valPair as IO.racePair with IOX and IOY. Now, in the case of IO race, the outcome, and I'm going to use spell pair properly. Obviously, that's a distraction. So in the case of race, IO race returns an IO with an either, with A or B. Now, because the loser IO is not canceled, but the fiber is returned, the either here is going to be a little bit more complex. Instead of A, in the case that the first IO succeeds and finishes correctly, you will get an outcome. This is called an outcome IO A, and a fiber IO with B. So this is what you get. You'll get a tuple in the case that the first IO succeeds. You'll get the outcome of the first IO that finishes and the fiber for the IO that's losing the race, so that you can do whatever you want with that fiber. And vice versa if B wins. So you get a tuple with fiber IO with A in case A loses, and outcome IO with B in the case that B wins. All right. Now, if you want to check which of these succeeds, you'll do a similar flat map like you did with the first IO. So I'm going to have pair flat map, and I'm going to have a case left, and I'm going to spell flat map properly, and that's not a distraction, that's a compile error. And in the case you get a left, you'll not get just a value that's returned by the winning IO, you'll get a tuple. So I'm going to have a tuple with the outcome A and fiber B. Now, in case A wins, I'm going to say fiber B dot cancel. So cancel. And then I'm going to sequence that with IO saying the string first task 1. And then I'm going to call it debug. And then I'm going to sequence that with IO with outcome A dot debug. And in case we get a right with fiber A and outcome B, I'm going to do a very, very similar thing. So I'm going to copy this and I'm going to say fiber A canceled. And I'm going to say second task 1. Of course, I've misspelled fiber A. I don't know what's with me on this video. I'm misspelling a bunch of stuff. And I have IO with outcome B with debug. Okay. Now, I'm going to give you a small demo here. I'm going to start 2 tasks taking a different amount of time. So this snippet, this function here with demo racePair has a similar mechanics to race. The loser's fiber is cancelled and the winner's result is surfaced. However, the power of racePair is the flexibility it provides by handing you the losing fiber so that you can do whatever you want with it. Maybe you want to wait for the loser 2, maybe you want to give the loser 1 or 2 or 10 more seconds to finish. There's a variety of options for you to pick. And so racePair is one of the more powerful calls here in Cats Effect 3. Now, let's run a small example. I'm going to call IOX as IOSleep with say 1 second, and I'm going to use the as function like a small flat map to put the 1 number inside here. And I'm going to call on cancel, so I'm going to attach a small cancellation listener here, and I'm going to have an IO first cancelled, and I'm going to use debug void, and I'm going to do a very similar thing with another IO. I'm going to call this IOY, and I'm going to sleep 2 seconds, and I'm going to put the number 2 inside so that we can make the difference, and we'll say second cancelled in this on cancel listener. And in the run method, which is our main method, I'm going to have demo racePair with IOX and IOI. So do this, and I'm going to simply call void here because I have debug basically everywhere. So I'm going to Control R. You can right click and run your application if you're on a final version of Scala 3, depending on when you're watching this video. And let's see what we get here. So we have second cancelled, first task 1, and we have succeeded with IO1. So we have first task 1, and then we have succeeded with the output of the first IO. So this was a beginner-friendly video on how you can race IOs running concurrently, how you can employ the timeout pattern either with your own manual version or with the Cats Effect version, and how you can use a more powerful version of racing that allows us to more flexibly process the results of concurrent IOs. I hope you liked this video. If you did, go ahead and click the like button for me and subscribe to the channel for more videos like this. I'm also going to link in the video description the link to the Cats Effect course when that's coming out. And in the meantime, check me out on Twitter and LinkedIn for fresh updates on upcoming material. Now, I'm dying for feedback, so please leave your comments to this video. I read every single one. And check out the Rock the JVM website. I have tons of content on Scala and Akka and Apache Spark and Cats Effect and much, much more over at Rock the JVM. And until next time, Daniel signing off.